Hi, hello, everyone. Welcome to today's data learning talk. Today we're very happy to have Mateo Neira from University College London, and he will talk about graph representation learning for street networks. Mateo, the audience is all yours.
Well, thank you, Sifa, for the invitation and for the introduction, and good afternoon, everyone. Before I start with the presentation, I first want to introduce a bit of why we're looking into street networks, and for those people who might not be too familiar with kind of urban science and street network analysis, why it's relevant. And then I'll present two different pieces of work. So the first one will be related to some initial work that was how this graph representation learning for street networks kind of started, and it was on unsupervised learning using convolutional autoencoders for street network unsupervised learning, and kind of the limitations we ran into that, and some other research that has been published around that topic, also running into a lot of limitations, and how we kind of went down the graph representational learning as a way to get around those limitations. So first, just as a motivation for the work, is street networks as a source of information. So I think since around the 60s or 70s, people realized that we can get a lot of information about urban environments just by the way the street networks are laid out in cities, because they tell you a lot about the connectivity patterns between different areas, and also to restrict kind of the movement that people can have within different cities and within different areas. And that in turn influences everything from location of retail and businesses and residential areas, all the way to like segregation patterns and how different populations can mix within different areas. And traditionally, how this has been studied is by abstracting away these spaces into networks where there's kind of different ways to represent them, but usually treat street network intersections as nodes and streets, connecting those intersections as edges, and then running different types of graph analysis or network analysis on them. So to try to find where are the edges that have the most shortest paths passing through them, or what is the average kind of distance from one street to all other streets. And that gives you a lot of information about the general urban pattern. And there's been a lot of research kind of tying in how these different measures, network measures, relate to where different businesses locate, where residential areas tend to be, and things of that sort. And as I was mentioning, this can give you a lot of information about not only the connectivity patterns in different urban areas, and in turn, what kind of transport accessibility and economic opportunities you have, but also you can estimate travel patterns because people tend to use the shortest paths more often than not. So just by looking at the connectivity of the network, you can infer kind of travel patterns, land use distributions, and there's been a lot of work also tying in these sort of network analysis on the street networks with kind of urban form of different areas, and trying to understand how different cities develop, and also kind of classify different cities by the types of networks that you see. And that is kind of what motivated the initial piece of work, which was looking into ways in which you could use machine learning algorithms for an unsupervised kind of learning approach, where you wouldn't have to feature engineer or look at specific graph features and try to correlate them, but rather have a black box try to abstract the most useful features and then use those features in downstream tasks. And the way this is, the data that we're usually working with is we have different types of street network data sets. So that could be like a base map, as you can see here, where you can get the street surfaces or polygonal kind of partition of that space, in turn generate kind of road center lines from these, and then generalize these center lines to kind of simplify the network. And then you can represent these geometrical features as graphs or networks that then can be analyzed in many different manners, which I've just laid out a few here. But the most common one is just treating junctions as nodes and the street network, the streets connecting these junctions as edges, which is usually known as like primal graph representation of streets. And that's what we're going to be working with here. And so there was around 2016, 2017, there was some researchers that started looking at using these machine learning methods to analyze street networks. One of those first pieces of work was by Wahid Mosavi from ETH Zurich, where he downloaded street network data sets from different cities around the world and used a convolutional autoencoder to create latent representations of these street networks, and then ran some clustering to try to classify different kind of urban formations. And I just put an image here to kind of exemplify that. And following on that work, there was some similar studies at UCL from the same department that I'm working in by Gira and Roberto Murcio, which did a very similar type of work by using variational autoencoders. And both of these works and the work that I'm going to present after this, the way these street networks were handled was once you had a kind of simplified center lines of the roads, you created a raster of that. So essentially an image that can be fed into a convolutional autoencoder, and you can just learn some type of latent representation that can then be analyzed. And one of the initial questions we had when we started looking at this and the work that was being published was, what is that latent space representation learning? Is an image of these networks enough to capture kind of the complexities of these networks? Because the network doesn't have any information about the topological kind of properties, the connectivity patterns. It only sees pixels. So we published this paper back in 2019 with Stephen Law that tried to answer that question, and it was we wanted to know, what compact representations can be learned from urban images, and in the paper we did both street view images and street networks. Here I'll be only focusing on the street network side of things, and then looking at these latent representations from a geographical perspective to try to understand what that latent space is actually capturing, and how you can use what that latent space can be useful for. So to do that, what we did, we just had a simple variational autoencoder where you had, again, a street network image that was fed into a series of convolutional network layers to get a final latent space, and then passing that latent space through a principal component analysis to get kind of what components of that latent space presented the most variance and were like most important to the network, and to kind of disentangle them. And then we can kind of start to interrogate the latent space by doing latent space perturbation and also some geographical mapping to try to understand what the network is learning from these images. And this is essentially what we had. So we trained the model using the same data set as the previous studies I talked about. And after training the model, we can then integrate and look at the average of the principal components of all the latent spaces of all the images in our training and test data set, and try to understand what those latent space is capturing by doing some latent space perturbation. So just moving the values along in the latent space, refeeding it to the model and regenerating the images, and we get something like in the bottom image here, where we can see that mostly in the first layers, and we will see that in the next slide. In the first layers, the network is mostly capturing kind of spatial densities. First, just kind of generalized spatial densities, and then kind of spatial densities located in different areas of the grid. And the local structure and kind of what you could think of as connectivity patterns of the streets weren't really being captured into very late in these principal components, and weren't contributing much. So we hypothesized that, since the network doesn't get direct information on the topological kind of structure of these streets, it's really not able to abstract that data just from the images alone. But you could still get some useful information just from that approach. And this is the case of running that on the city of London. And you can see that just with the first principal component of that latent space on different graphs of the city, you can start picking up like different city centers or urbanized areas, such as like the city of London or Croydon down in the bottom. But again, we were hypothesizing that most of what the network is picking up is actually just densities of the networks, rather than anything more meaningful that could be used in other types of analysis. And this is what I mean by picking up maybe first the global densities in the first components, as you can see here. And then as we go down, the rest of the principal components, kind of more spatialized densities. So going either is the network more dense towards the right or to the left, or towards the top or towards the bottom, center to periphery, kind of diagonal densities, and mixing all these components, you do get some differentiation of different types of urban formations, but not anything compared to what you would be able to get by running actual analysis on these graphs and retrieving more complex features, such as the network connectivity patterns, or running between a centrality and understanding how these values are distributed along different areas. And so, we saw that through these kind of methods that people started using these convolutional neural networks on rasterized versions of the street network, there was a loss of the topological information. That's actually very important for street networks. And also, if you wanted to use these networks in any generative kind of framework, which could be useful for a design, or also to try to see if you can generate some sort of like null models, with these approaches, really couldn't be done, because a lot of information is lost in that kind of conversion of the graph into an image, and then converting that image back into some vector representation. And so you lose both topological and geometrical information. It's not really useful for kind of generative, as a generative model. So with another colleague, we wanted to kind of look at what ways we can get around these issues. And right around that time, graph neural networks start to become popular, and you can actually start using them with our data that we had. So we wanted to see how can we use these graph neural networks to try to learn more robust representations of the street network that preserve both the topological and geometric information. And also look at then how can we assess these embeddings in terms of how it is able to reproduce kind of similar networks seen in real cities. So can we actually use networks trained with street networks in a generative model to generate kind of synthetic streets and compare that to kind of the pattern statistical kind of properties that we see in real world networks. And this is the general architecture that we came up with. And yeah, I put the name of the paper that we have. It's right now under review, but we have a preprint in the archives if anybody wants to kind of dig deeper. But in a very general sense, it's composed of two different modules. So a spatial module that's actually using a transformer to learn the spatial distribution of street junctions. And then a latent representation that's learned from that spatial module is then fed into a graph module that has these graph convolutional layers as an encoder, and then just a simple decoder that outputs a fully connected graph with probabilities of edges between nodes that then we can just threshold to create an actual graph. So in this case, the objective is to learn this robust embedding of a graph, which is basically just a series of vertices. In this case, are street network junctions, the edges, which are the streets, and this attributes of the junctions, which is basically just the actual spatial location of those nodes. So you can think of just the latitude and longitude of the street intersections, which is then normalized. And the graph is basically represented by adjacency matrix, saying if there's a street or there's no street between different junctions, and that attribute of the location of those nodes. So for the spatial module, we had to do some interesting data pre-processing to actually be able to use a transformer to output these probabilities of nodes, where we create or learn different embeddings for these XY coordinates. So we feed in a sequence of coordinates that is actually kind of the X, the Y of each one of the nodes for a particular network. This position, a position vector, which basically just says what number of nodes this is, and we adopt a canonical ordering where we just say the first node is the bottom left, and then we just kind of order the nodes as we go from left to right and down up, just to get a consistent ordering of those values, and then the actual value for the X or Y coordinate, which we had to do an 8-bit encoding on, so we can use just some a categorical prediction on these and learn these this latent embedding that then we can use both to output predict the sequence of nodes, or also use to create or to feed into the graph module to predict the probability of then an edge connecting to two different nodes in the network. And to train this, we basically used the same data set that we had used in the previous paper we did with convolutional convolutional autoencoders, which is using data from OpenStreetMap, which basically has street network data for most of the world. It has like 85% coverage, and we just got all the data related to cities and towns, and then we subset that further to just cities and towns with populations over 10,000, just to avoid getting like very rural areas in our data set and kind of skewing those results towards non-urbanized areas. And this is kind of the distribution of those places of the data that we were looking at. And on the right here is the actual networks that we were working with from these areas. So one of the problems we have with, both of the convolutional neural networks on rasters and with graph neural networks is that we're really restricted by the size of the network currently, because it's very computationally expensive to run training on these. So we were constrained by right now a 1-to-1 kilometer grid. So for all of these cities that you see here, all of these dots, all of these 4,000 cities that we use for training and validation, we only get a 1-by-1 square kilometer area for that centroid of that city or town. That's kind of what we're representing here on the right. And with that data, we just split the data into a 80-20 split for training and validation. And then we just did cross-fold validation within our training set during our training. And once the network was trained, we were able then to just generate synthetic street networks. And this is what you see here on the left. So the network does learn kind of the general structure that it sees from our data. And we also test that against the actual statistical patterns of the data we see. So are the networks generated kind of similar properties of those observed in our data set in terms of the average street length, for example, or average number of nodes per edge. So kind of more reflecting again the density of those networks, and then some more nuanced kind of measures like average circuity, which basically gives you a measure of how straight the street networks tend to be versus how kind of more maze-like or complex they tend to be. And then also some more geometric kind of statistics on these. So the average form factor, which we derive by creating by getting the faces of the graphs, which basically would represent blocks in a city, and looking at the average size in terms of its area, and these two other measures as well, which is the form factor, which is basically just a measure that tells you how round or elongated different blocks are, and average compactness as well, which is just kind of the ratio between the block area to its perimeter length. And we see that the network is able to kind of learn fairly well the distribution of our data, and it could be used to generate synthetic networks just as is. So just a lot better performance than what we can get with other approaches, even compared to traditional network approaches that is seen in the literature. Although we didn't get to test these against these baselines, and that's something we want to do in the future to develop test against kind of traditional network approaches to generating street networks. And the last thing we did was, again, look at how can we use this latent space, and if the latent space can actually help differentiate, for example, different types of urban settlements just by the network layout and what the network is able to learn from this connectivity pattern. And this is basically what we did is we took that latent representation learned by the graph encoder module and we concatenated it to just form one vector and ran a principal component analysis again, and just took the first 600 or so components, and then just ran a simple k-means clustering to see if we could kind of get any sort of spatial patterns that kind of match what we would expect. And surprisingly, as you see here in the map, just from the latent space, you can start seeing some trends of the network being able to differentiate, for example, American cities from Chinese or Indian cities, or even places in Latin America. And again, it's kind of when we dig in further into trying to understand what the network is actually picking up on. Just to show you a comparison between two different clusters, it is able to kind of differentiate based more on this connectivity pattern and the kind of overall structure of the street networks. So, for example, creating a clear distinction between more of this kind of organic, and in many cases, kind of more historic urban street layouts that are much more complex versus, for example, the more gridded patterns that you tend to see in newer cities and prevalent a lot in the US as well. And this is kind of where we are at the moment, and in future work, we want to see if we can condition the model to be able to kind of guide the generation, because at the moment we're just able to generate kind of random street networks, but we're not able to kind of guide the network in any sort of way to generate specific types of street networks we might be interested in, and that is kind of a direction we're looking to explore, and looking at other ways where we can actually interrogate this latent space and see if it could be useful to tell us something or give us insights about these urban places and urban areas, and how it compares to kind of traditional network science approaches in the urban science literature. And I think with that, I'm done, and I'm open to any questions or queries that people might have, because I know I might have gone through that very quickly.
Yeah, thanks, Mateo, for the very nice talk. It was very clear and very inspiring as well. So for the audience, in case you have any questions, please do not hesitate to raise your hands, and I will let you to speak it out. Or you can type your questions in the chat, and I will read that for Mateo. Yeah. So actually, I can start. Meantime, I have several questions. So first, I'm curious to see what is exactly your latent space looks like. So when you said that you have an encoder to encode a graph, then latent space, what you mean the latent code is a vector, right? Or it's like a subgraph? Yeah,
no, it's interesting. I can actually share my screen again with that. Let me see if I have that. Yeah, PowerPoint slide. Yeah, sorry. So the latent space we're actually exploring in that here is this represented here by the Z, which is the latent space, the latent representation learned by the graph module, and it's actually not a vector but a matrix. It's still kind of just a smaller matrix than the one we're feeding into the encoder, and what we're actually doing to then explore these latent representations for each of the cities is we're actually just concatenating, so kind of flattening this matrix into just one long vector.
Okay.
And then running some dimensionality reduction basically to be able to make it more kind of manageable.
So if I understand well, here you're using encoders not for the purpose of like dimension reduction. It's more for the feature extraction from the graph, and then you can use that to perform, like, you present like unsupervised clustering, etc. Did I understand?
Yeah, Exactly. So in this case, this graph convolutional layers in the encoder are basically doing feature extraction, not so much dimensionality reduction. I mean, this the graph that the network, the matrix that we get in the latent space, it is smaller than the input a matrix for both, because for the input of that graph module, you have both the matrix that encodes the graph structure, so just the adjacency matrix, plus a matrix that contains the latent variables for each of the nodes, which is coming from the spatial module. So you're actually feeding two distinct matrices, and these graph convolutional layers are doing feature extraction from those, and then kind of combining that into just one single matrix that then we can just flatten and then run additional dimensionality reduction techniques to then be able to explore either by clustering, which is what we did in this case. But for future, we want to see how else we can explore that latent representation that we're learning.
Okay, and just a following question. So I think you present that your results with different cities. I imagine that you have different number of nodes in these different graphs. So that means you have different size of your A matrix. And did they share like the same size of the X, like the first latent space in the input of your graph neural network, or it's like it's with different X? But anyway, you can like input a graph, like no matter what the size of the graph is, and the X which represents your nodes information. And I mean, even if these dimensions are different, you can still proceed with the GCN after that.
Yeah, so you are right that the number of nodes and the actual sizes of the graphs differ from cities to cities, because what we're keeping constant is this 1 kilometer by 1 kilometer kind of grid, and then within that, you have areas where you might have just a couple of or a very sparse kind of network, and some areas that are very dense, so very different in terms of number of nodes and number of edges. But just to give an idea, the mean number of nodes is around 430. But there's a lot of variance for that. And to tackle this, so the network is able to take on different sizes. But how we do it is by feeding in a mask matrix to both the spatial module and the graph module. So basically, we set up
to be the same dimension that by putting the mask.
Sorry?
I mean, do you mean like you're putting the mask to enforce them to be the same dimension? Is that what you're?
Yeah, exactly. So the network has a max kind of size or a standard size of a matrix it can take, and then we just handle the different sizes in the data by using this masking matrix.
Okay. Yeah, thanks, Matthew. And meanwhile, actually, I have another question, more related to the applications. So I was wondering, instead of like the generative models and the unsupervised clustering that you have presented, have you either sought or tried to use that for other downstream tasks? For example, to predict, to predict like the cars in these street networks, to like some sort of the debate in this network, or like to make a dynamical prediction, but this is just an example. I was wondering if you have ideas for other downstream tasks.
Yeah, we actually haven't explored this much. I mean, there actually are some papers published that are doing this. So using this to predict like traffic flows, for example, in the network, and that could be an interesting approach. In the first paper that we published with Stephen Law, we were just like unsupervised learning for geographical data. There we did do something to see if you can use the latent variables to predict other features such as house prices or street dimensionality as well. So like street widths versus like street heights. But that was working on the street view images side and not so much on the street network side. I mean, it is something we are interested, but we haven't had time to explore. And there are some interesting works that have shown that you can use these latent representations as predictors for other types of variables.
Okay, yeah, thanks, Matthew. Let's see if there are questions from the audience. I don't know why, but they're so shy today. Maybe it's the end of the day. Yeah, so actually, I have maybe one final question. It's about when you said you can perform this clustering, because at the beginning, you're presenting some methods that treat the graph as images, right? You use that just like use a traditional convolutional neural network. So I was wondering, have you compared the results of your proposed methods and the traditional like CNN methods like Bayesian autoencoder or convolutional autoencoder to perform this clustering inside latent space, to compare if your methods outperform like the traditional approach in terms of unsupervised clustering? Yeah,
so we started looking at that. The problem we ran into is having an actual measure that we can use. So because at the moment we can do kind of more subjective kind of evaluation of the clustering results. Because the main problem that we face is we don't have any ground truth to these that we can compare against. Because there's basically no data set available that has classified different types of street networks based on some like principled way. So you have a lot of papers or methods proposing a way to classify streets or classify urban areas based on the street networks. But there's no clear way in which you can compare like which method of doing a clustering or classification is better than the other, at least none that we have been able to find in the literature, or that we have been able to think of ourselves, that we might be able to get an actual, quantifiable measure.
Mm-hmm. Okay. Yeah, thanks, Matthew. I can imagine that can be quite difficult to find the ground truth, since you said things that didn't existed before. I think there's a question from the audience. So hi, Matthew, thanks for the talk. Slightly off topic, but how would this methodology apply to futuristic vertical cities like the line in Saudi Arabia?
It's a good question. I think I would have a lot to say about the line. I'm not sure about like these vertical cities. It's actually quite interesting to think about. But just talking more general about like future cities or new developments, it's something we are exploring, and that's why I mentioned that we were looking into how you can have a way to guide kind of the generation process for the synthetic networks. Because one of the things that's kind of a lot of people are looking into, and it's very useful in practice, is to be able to generate kind of different options or different street network layouts for a new development, let's say. So there's a lot of like new cities being built in China, Middle East mainly. And in the future, we'll see probably a lot of development happening in Africa as well. And these are, new designs, and you need ways in which you can explore kind of your design space. And for like buildings and smaller scale projects, there's a kind of generative kind of approaches that use genetic algorithms and such to produce kind of thousands of options, and then run some key performance indicators and the different metrics to try to pick out what the best performing ones are. But in the case of like large urban areas, one of the first things you start with is these road networks, and there's no current method that produces kind of realistic and feasible street networks. I mean, not even the traditional methods kind of are very useful in this case. And I do see kind of a lot of value in these generative models if you can find some way to guide them and make it and constrain them against what kind of like the designer intends, then they can be super useful. for design exploration purposes.
Okay, yeah, thanks, Mateo, and thanks, Cedar, for the question. So if there's no more questions from the audience, I think we can stop the seminar today. So I'd like to thank again Mateo for accepting our invitation and for giving such a nice talk. And thank you everyone for joining us. So yeah, looking forward to seeing you to the in our data learning talk next week. Yeah, see you everyone. Have a nice evening.
Thank you, everyone.
Bye.
Bye.